So the topic that we were trying to set up here today is the system design level of these more complex heterogeneous devices. So when you're talking about these devices, it's the adaptive SoCs, and basically what I want to talk about is how these whole different aspects of the design work actually come into the complete deliverable product. So that's the actual focus. Before we are going into the details of the talk, let's first also mention what PLC2 actually is about in the market. And now you have reached us through the webinars that are part of the training and coaching department. That's on the left-hand side. Basically, this is where PLC2 started as an overall company, from the approach of bringing the expertise to handle these complex devices of the programmable logic back in the 80s or the 90s rather. 80s and 90s, and then basically bringing it to the engineering community just to really deal with all the different aspects since then into our now highly complex devices of the adaptive SoC department. On top of that, we developed customer-specific projects as well. So you see the middle column, you can actually ask PLC2 to help you with the designs. And that basically scales into different aspects. So for once, after trainings, when you're going into, like from this webinar into some trainings, you will be able to also meet with us as a consultancy service, so that just like you get the right level of your learnings from the training into your actual projects. So this is what we're talking about under the development services, but up to the level where we take on complete product development. For once, we have our own products in the market, of course, but we also have product development support for different companies at hand. So you can ask us on many different aspects of deploying the AMD device portfolio, and we will be ready to serve. Okay, from that perspective onwards, let's look into the details of what I was promising before with this nice title, talking about heterogeneous devices first place. And this is why I need to actually also come into short, brief description of the overall device architectures and what they actually mean and what it has like an influence on the design flows overall. And that will mainly be concerned about this idea of the platform level designs that you're doing through the tools and the tools that are offering to bring these different aspects of the devices together in a proper way. And hopefully we will be able to get the insight into how such a design looks like in Vitis overall. And one very big aspect of this is to also understand that you cannot only just do these things based on hardware that you have already, but you will also be able to evaluate what you have been creating from the set before you actually need to go to the hardware, which is an ever more important aspect for these complex designs these days. So let me try to introduce the idea of heterogeneous computing overall. It's actually not that new, but so far what you would use is basically you would stick different devices on your PCBs and bring them like together to talk to through certain interfaces and actually do the different jobs they can, because you have these kind of very distinctly compute models for the distinct aspects of your designs. So for once, you will be surely aware that you can have embedded systems that would traditionally simply just work as a traditional processor CPU, like instruction set-based imperative programming. This means you're strictly following a path that you have been thinking along. And if you have to do multiple things, you would sequentialize them out. So that's the very traditional way of programmable processing units like the CPUs as they are, but in the end, you're structurally just bound by the number of CPUs that you can have, or structurally bound by the instruction sequentiality that you have. Now, what we have for a long time already in the AMD portfolio is that you have the PL part, the programmable logic part, that is there as your adaptive engine or your adaptive programmable architecture, where you can actually create any kind of parallelism, any kind of special sequences that the CPU instruction sets don't offer you. So it's a very distinctly specific implementation that you have to do in order to compute something at all, first place. So it's a different approach than these like straightforward instruction set things that you know from the CPUs. But then on top, where CPUs don't shine, is just the simple repetitive tasks that could even be parallelized out. So this is where the vector processors come in. And this basically is the idea of these three compute domains. Basically, you can attribute any of your tasks into any one of these three domains. and you would basically just pick the right tool for the right job if you can. But so far, this would mean you would have to add these different implementations on your PCB in a certain way. Well, of course, you get the CPUs, as we will see, together with the adaptable logic, the programmable logic, already out of the AMD portfolios and maybe other portfolios as well. But in the end, the combination of doing something like the vector processing on top, in line with everything, that's actually the kind of third level of computation that you want to see. So what is it when I'm talking about the kind of aspects of computation? If you see this code right here, that's a pretty trivial nested loop of convolution. So in the end, what you see in some expression in the middle, you will find that there's one singular and linearly independent expression that I'm computing in the innermost loop. And then you would basically have to repeat this over and over in order to filter across an image, for example, as in this case, it would be your convolution filters of a certain size being drawn over the actual image size, and then you loop into both directions, and maybe in the end you have multiple planes of things to calculate. And that really means in the end, the complete nested loop depth is what your CPU would traditionally compute in a sequential fashion. So this like takes a lot of cycles, but actually this guy is not doing too much different things at the time. And this is where you can do it with the CPUs, but you're not quite efficient. What would happen in a hardware, if you would be placing this code in a certain way into an HDL code, you would replicate this compute expression in parallel. And you would by then simply just get the same result. Instead of waiting for n cycles for this loop to be traversed, you would get the same result within one cycle. And the same approach is there within the vector processors, depending on the actual instruction level that you have. So just keep this kind of model in mind. That would kind of help you to provide a certain compute distinction that you want to bring into your portfolio of the actual design. So again, revisiting this idea of we have these three different aspects of computation. You have the very traditional sequential processing model of the CPUs. And that's really all the CPUs that you know, like maybe the larger ones are kind of pretending to be faster in a way or be more efficient in a way because they have some means of vectorization already with it. But in the end, it's not really scaling compared to when you look into the vector processors where you have a more slim and more focused instruction level, a very parallel higher density kind of computation. So this is what you would expect from the GPUs and all of these kind of elements in between. These guys cannot do the highly sophisticated instruction set stuff that the CPUs can do, but in the end, they would still be available in a much higher density and a much higher parallelism. So we're talking about thousands of cores compared to talking about a few tens in the CPU level in this case. And now the programmable logic is just the workhorse of most distinctly implementing anything in there, because you can put CPUs in the programmable logic, like soft core processors that you can have, and you can have vector processing designs in their parallelism of implementations that would simply just do a very distinct instruction in this case. So it's really important to understand that these variable processing parts typically would go into the FPGA side. And one part of the adaptive SoC portfolio of AMD is the Versal devices, because these guys now finally bring everything of these three compute domains into the market within one device. So you can have Versal adaptive SoCs that hold the vector processing elements as a hard IP, a high density vector processor array, as we will see in a moment. And you will have the CPUs, and the CPUs scalable up to also a high number of CPUs in this case, basically the Versal AI Edge Gen 2 devices coming in with up to 8 APU processors and 10 RPU processors, so the processor cores from ARM, of course, in this case. So you have a widely scaling CPU part, you have a widely scaling vector processor part, and you have, of course, the traditional FPGAs with that. So that means in the end, what we're talking about is from the terms of the adaptive SoCs, you're talking about the processing system, or PS, inside the Versal devices and the Zynq Ultrascale devices. You talk about the PL, the programmable logic, as part of the adaptive SoCs overall. And for specific devices, you will be able to keep and grab the adaptive AI engines in the complete systems. So what the overall adaptive SoC architecture brings into the market is basically two families right now. Well, these are all settled on the earlier advances of Zynq 7000, but in this point, like from a more complex design perspective, we're talking about the adaptive SoCs more on the Zynq Ultrascale side and the Versal side, which is in the end then multi-core processing system. As you see on the top, this complete block here is really what is there as a hard IP on the devices. You have the application processing units like the CPUs that are more like a coherent worldview processors that can be clustered together to take the same tasks, which is basically something that you would use in an operating system like Linux as an SMP, symmetric multiprocessing element. And then you have other processors accompanying this complete thing, the cluster of real-time processing units that are actually there to help you with predictive latency accesses into your systems. Whatever you need to control in a certain time frame would need at least to be countable. So that's the kind of approach that you take in here. These clusters of CPUs are there in these adaptive SoCs to take on different parts already within, or different tasks already within the CPU system. So you have additionally co-processing elements like the GPUs. The GPUs may be differently available in different devices, so you have to be careful about like your requirements for it because they scale the kind of device family that you can use. There's even now GPUs on the horizon with the Versal AI engine, AI Edge series Gen 2 that actually has GPUs yet again where the Versal Gen 1 devices didn't have. So this is really what you have to look into when you deal with these device sources. You have a lot of infrastructure based like interfaces for your housekeeping that also comes with the CPUs. So you would basically use these to do your overall control flow of your board, for example. But then for the specifics, for your actual mission mode processing that you want to do, you have the extension into the programmable logic. And that's really kind of the most flexible thing. You're not buying an IP in the end from the PS part, like from the hard IP part for your designs. You may have a very distinct data flow from transceiver-based inputs to transceiver-based outputs with logical operations in between that you need to do. And these are basically there to give you complete flexibility in there. When we look into these setups, you can also see the challenge that you have to do is basically you will have to program the CPUs in a proper way in order to use whatever the programmable logic offers. And there's structured design support from Vitis and the tool flows that basically allows the CPUs to well understand what is there in your setup that you have created, and you have a register-based flow between the two sides for control flow in order to set up things or know about the operation inside, the state of the operation inside your mission mode logic. So that's the kind of core idea of the system design with these devices. When we're looking into Versal, it comes like on the Zynq Ultrascale side before, we saw like this upper and lower part for the PS part and the PL part being shown. Like here, you have these three distinct groups of elements. You have the processor systems, that is a more capable processor system with the clusters in there and growing for the Versal family, of course. You have the programmable logic being highly dense compared to what has been there in the Ultrascale world. So that's a 7 nanometer process at this point, and it's kind of more efficient also from a logic implementation. But then you have this distinct block of AI engines that are giving kind of away the vector processing elements. And what you see from this complete diagram is all of these three elements are efficiently connected through a programmable network on a chip that basically covers the DDR controllers. So that we just go back again. The DDR controllers are not exposed anymore through the PS part of the Zynq Ultrascales, but they are directly exposed to any of the designs you do. So you get a more efficient control over data flow. So there's a lot of architectural things that we cannot mention at this point. From our perspective, it's really just important right now, system level design, you're doing three distinct tasks in order to split your application between the different provisions of the devices. And what's important to understand, of course, is that this all will need a complete tool flow in its own right in order to get these things under control. As for the AI engines, just to make you aware of the architecture of these devices, it's really an array of vector processors that is arranged in a particular data movement grid in the end. So when you see these arrows in here, all the arrows mean some data traveling between different elements. And of course, if you want to parallelize out your computation, exactly the data distribution is this one thing that you have to solve. What you see is that within such a tile, AI engine tile, you have local memory each time, and you have the actual processing module that is there to do the vector operations inside. But these local memories are shared memories in all 4 directions. So basically, this guy can reach its own memory, or the neighbor to the right, to the top, and to the bottom, which quadruples the number of memory cells that you actually have, but in the end also keeps like independent accesses between the elements. And then you will finally see these independent accesses being mapped out to the vector processor that you have. It's a very large instruction word processor, so with one fetch, it actually catches quite a lot of different actions it can do. Doesn't have to, but in the end it can do. So basically you will have a RISC-based CPU, 32-bit CPU already within that block. On each and every of these tile members, you already have a traditional CPU in there with the scalar unit. You have the vector unit with itself that is capable of looking on a wide array of data, a wide vector of data, and interpreting it as different numbers, and it would basically then feed through the vector unit. And you have all the support functions like moving data in between these items internally, or between the memory and the inside of the elements and the different memories. So that's what actually gives us the efficiency. So in the overall system design, you have these 3 elements. You have the CPUs, you have the programmable logic, and you have the AI engines. All of them are independently available on the device, but you have to organize the data movement correctly in order to get efficiency out of it. So when you look at this particular picture, this means already, for somebody who knows embedded systems out of the box, you will have to talk about actually creating instruction level components for the PS parts. It's just ELF codes, basically. You will have to create the bitstream level for the programmable logic. And these are actually going together. So some design information from the CPUs would need to hold to like the definition that you take into programmable logic, and the other way around also for the AI engine, because all of these guys need a certain exertion of control, and you will need a certain level of functional correlation between them in the end. So this means if you have a design flow that would barely look into the later elements that get integrated, you will be in quite some difficulty to create a proper design. So when we look into the design flow, we will have to talk about extensible platforms from any kind of step. So whatever you do in the tools at this point, you will pick your current design, you will wrap it as a platform, and you will use it in the next step. And one of the most prominent steppings there is that you start off with a hardware design that cannot by nature know what will be kind of asked of it until later only, because you have not defined the AI engine, vector processor programs and everything like that. You have not defined the CPU requests onto the hardware. So what the heterogeneous design flow actually offers in this case is you can create a very traditional hardware design in Vivado, but you will not completely define it in the sense that some things get attached to it later only. And that's the kind of discussion about the fixed platform designs that used to be there, showing in here, versus the extensible platform designs that we are having these days. So from the Vivado nature of the base project for such adaptive SoCs, you will start off with an extensible platform rather than a fixed platform. The fixed platform means really just you have a traditional hardware design. Everything is defined, including the, say, like internal settings of the PS part, all the clock frequencies, all the IOs that you're actually using and everything like that. you're defining that as kind of a configuration header file for the CPUs, and you're driving the bit stream next to it, and you have a complete design with it. Now, that's still available. If we look into, let me just see if I can find it here. Should be, yes. If we look into a very traditional design, you will see some symbol in the Vivado side for the PS part, and you will see some symbol for the PL blocks, whatever you want to do. And typically we would start, if we have a PS system, we would start to integrate through the block integrator to the IPI. So we would basically start off with creating a base platform on that level. Now, what I'm trying to show here is that the actual extensible platform that we're talking about is not too much different at all. So who knows these kind of tool flows may be aware that what I'm having in here is really just a PS system as a symbol. In Versal terms, this is called CIPS. It's not called PS only. So you would have that, and when you double click it, you would be able to edit the internal settings of your PS part. And then you get all of these other things that are kind of connecting to the rest of the world, which means in the end, at this point, we have an XI interrupt controller that goes to the PL. And if I would build that thing now already, it would give me a completely valid design on Versal, but it would not be able, it would not really bring any kind of function in there already at this point. So what we see overall, who's versed with these designs knows that this is really just a PS system being combined together through some interconnects into the DDR. So we have the DDR controllers to the NOC in here with the PS system. And we have basically some kind of very distinct, straightforward XI blocks inside the PL part, but no actual function. So this thing, this complete platform that I'm building in here is prone to be built up later on and be upscaled from what we have. So the block diagram at some point later on will be added from the software-defined parts that we will do in the system level design. So for these extensible platforms, you have these kind of setup features where you can basically determine which of the XI ports that are all around the design can be used later on to attach something new to it. That's kind of a metadata information layer that these extensible platforms gain from the Vivado process, so that later Vitis can pick up on these things to create more content. So let me just maybe claim that this process is not just there for Versal. What we do building an extensible platform, we can do this for the Zynq Ultrascales, we can do this for the Kria, SOMs, we can do this for any of these kind of adaptive SoC-based platforms, and it's the same thing. So you're building a HDL plus CPU level or PS system level configuration as a base that doesn't necessarily hold your final functionality. And then you go into a kernel-based development inside Vitis, software-defined development of these elements that you functionally want to have. And that's what we try to follow through by now. What's of course important to understand is, like, if you have an application flow, if you have a task to resolve, if you have a design to deliver, you would need to understand like which parts of things go where. And I was showing this earlier, design parts, that is nested loops that would basically just lend themselves to be like a parallelly executed thing. So then it would go into the vector engines, no matter if you implement them on the PL part or if you implement them on the AI engine part. So basically, when we look into the setup of a typical multi-data in kind of design these days, you will have some interfaces to your sensors of the widest range, and you would basically have to precondition whatever you get from these sensors. You would basically unpack data from the interfaces. You will basically precondition them in order to be properly worked through, like from calibration, anything from calibration to scaling and whatever. And that, of course, is very typically done through high-speed interfaces these days, and these are prone to like be in the programmable logic. So the kind of interface level will still stick easily with the programmable logic. Of course, you can have Ethernet-based transactions coming in through the CPUs as well. Then you would simply just put your results into the DDR memory, of course, and simply pick up from them. But when it comes to then picking up this data and doing the parallel analysis or whatever kind of image recognition functions or any of these kind of higher level data processing functions, you would try to go into a vectorized description, and the vectorized description would easily go into the AI engine. So when you have happen to have a Versal design in your level, this is of course what you would pick from your functions to actually map out to the vector engines in this case. And finally, if you have created some certain information out of your input sensor data, it would of course make perfect sense to have somebody dealing with that result. So if you're just doing some predictions, somebody would have to deal with these predictions and do something with it. Otherwise, it wouldn't have been worthwhile to do that part. So that's really the kind of setup that we can have in this complete, like one kind of representative design level. That's just what I said. But when we are looking into what this mapping actually really means, there's a systematic control flow behind it. And that would basically mean we have this notion of platforms that I was mentioning before on each and every of these cycles. So you can basically think about the devices of the adaptive SoC being split into PS and PL, of course. This is the more like basic division that you have. But now you already see that in this case, the AI engines are kind of counted towards the PL side. And that's basically owed to the fact that these guys don't have a native I/O interface. You can go through the NOC, but you can also, and that's the most likely one for high data amounts, go through the PL part of things. So what we create on the core structure of the device in order to follow our kind of application idea right now, it would be we would create subsystems that handle particular data flows. And in this case, these subsystems would basically be parts of your PL part that are actually also talking to the AI engines, and the data movement between them needs to be defined. When you want to do that, you will have to have a firmware that is actually really controlling these elements, because at some point, any kind of kernel that you're trying to start would need to understand where the data has to be fetched from and where the results need to go, and all of these kind of flow control things that you need to have in place. You can have subsystems with AI engines, you can have subsystems without AI engines. So basically the concept of these platforms and the subsystems will always build. So what we saw before, our naked platform that doesn't have design content needs to be filled by what is called kind of a system block in this case. And overall, if you have such a firmware that controls the particular kernels that you have, there would be typically the assumption of a high level, say application level code that controls the complete life cycle. That doesn't necessarily mean that it takes part in the data movement, but it needs to orchestrate the kind of interfaces to the particular computation, all of these kind of things. So that's really the important part to understand that we have to deal with in that regard. So when you are looking into the terms of platforms that I was creating, I was coining, platform is everything that you can package and reuse in the tool chains. So basically, if I'm starting to work on the application side, I may understand my firmware layer to drive the whole elements, and this firmware layer needs to convey the content of the complete left-hand side of the PL fabric and everything. So this firmware layer actually can access a representation of the hardware through software means, and that's what's called a software platform. It's provided by say like it's something that you create from the hardware side, from like you pick up your address map and you add the drivers to the particular items, and that's the actual thing that you have to look at. Then on the other hand, we have the hardware platform, and that really means that you need to provide this address map first place at one point. Now that can be created out of what we saw before, the Vivado tool flow that has this block diagram and everything is nicely written up and nicely connected there. But it can also be assembled in software-defined projects, and that's what we will have to look at in the next step. So when you look into these three different compute domains, like the vectorized compute, the arbitrary flexible compute on PL, and the PS compute, all of them will come with different tool flows, of course. So you have all kind of base information that you need to go into, and you will basically then have all the different tool flows to translate these information, like source codes or models, whatever you have in this case. There's a lot of different tool flows that can map out to the different endpoints. Very typical, of course, for the ARM-based CPUs, you will have a GCC or even an ARM compiler in this case that would simply just create the ELFs. You can create the ELFs for a single core bare metal, but you can also create them for Linux operating systems that abstracts away the number of processors you have. So any kind of this is possible, but it's the GCC flow that's the important thing. In this case, you would not be able to use that flow to create the HDL side. And that's basically why you have a distinct project flow for these kind of targets. You have the AI engine array, and we saw before we have these singular vector processors, but on top we have the task of computing or taking care of the data movement. And that's really what you get from a proprietary toolchain. That's the AI engine compiler. There's kind of a C++ API level that takes care of both vectorizing your functions as well as taking care of the movement of your data, which is a kind of interesting model compared to what we have on the standard C compiler side, because you will have to vectorize and use APIs to vectorize your code, basically. And on the other hand, we have still the PL part to fill. And the very typical thing, if you are working from a software-defined context already, is that you are picking some higher level modeling like HLS. HLS would pick up your C function that you would traditionally run on your ARM core and will cast it into HDL code for you so that you will get the hardware to work for you instead of the CPU instructions. It's kind of offloading the work from the CPUs, and when you combine it with the data movement descriptions that you need between these different worlds, you will be able to kind of create the correct elements for each processing part. Now we have these three different projects, three different compiler tool chains that are completely disjunct first place. So we need a software definition to create our subsystem, and that's exactly the next step. So the kind of tool chain allows you to combine these different elements into a runnable design, which means we have a linking step that picks up the CPU ELF code, that picks up the AI engine content as a configuration data for this array and the ELFs for the singular vector processors. And we would also have the bitstream or the overlay bitstream for particular parts of your hardware. And with this system linker approach, you can create final development outputs like your artifacts that would be able to be run on different targets. So you have to kind of tell this linker process what you are trying to achieve. Do you want to just do functional run in development host execution? Do you want to run it as an emulated version of your true created artifacts, but still on the development host? Or do you want to run in hardware? So basically, this is the kind of main central point where you kind of decide in which output direction you go. And you can create all of the different targets always at once. I think from a design thinking perspective, it's always about closing functional performance first, or functional focus first, which means you can stick on the local execution, going into, say, like context of different of these elements running together. You can look into the system simulation level, and when you really want to see what's going on, you go into the hardware finally with the overall setups there. So in order to get this whole thing straight, you will basically have results from your executions that you do, and you would basically go back into your different tool chains in order to achieve a more appropriate outcome of it. So that's the kind of thing. When we look back into the Linux world, I have created at some point, just to show such a project. When you look at it right now, let me see if I can make it a bit more readable in this case. You have a complete workspace in this case. This workspace actually lives there to hold the complete items that you saw on this slide before. So we have an AI engine component. Vitis, the toolchain that we're talking about here, is always talking about components, no matter what you do. It has an AI engine component. It has a development host program that actually needs to do its job. So that's the CPU code for it. And it has HLS kernels. So if we look into these kind of things out of the box, that's also, if I'm using HLS to create my HDL code, that's also a C code. So basically you will find the C operations. You will basically be able to address the different input-output interfaces from your function signature, and you will finally see how this whole thing operates internally. In this case, it's reading from an addressable field, streaming out into a stream. There's another kernel that's just doing the other job, like putting in a stream and mapping it out to memory mapped interface. And we have the AI engine component that by itself also has very much the particular API descriptions of such data movement items. Well, that's the bad part. I should use the header in this case. So what you have in there is a particular description of kernels that you are listing. These kernels would basically be mapped out to the particular AI engines. I don't necessarily want to show the code behind the scenes at this point, but in this case, it really means that you have these three kernels being connected together in certain ways, all these connect functions. So that's the data movement description that helps you to kind of build a mesh across these AI engines. So that's really the kind of approach that we have in there. So we can have basically a short look into what this really means. So the tool operates on these kind of functions that we have, and the graph description was there to have 1, 2, 3 kernels in there, and it shows the connectivity that we have achieved from there. So that really gives you the way of like how this matrix of AI engines is set up and how it would basically be used. So that's the one part. And the additional part on top that of course is needed is the development host, or in this case, the target already. That's C code that basically, of course, in this case is a Linux-based C code. It has a main routine. It basically then goes through negotiating with the hardware underlying in the subsystem if it's really what is there from a, say, like, do I expect this to be this kernel or whatever. So there's different ways of communicating that. And then there is a lot of elements going on with allocating memory and conveying the addresses of these memories into these particular parts of the subsystem. And then you have the flow control of these particular things. So you will see that you carry out the kernels at some point, and you would basically be also carrying out the AI engine execution. And all of that is part of your host code. In this case, we are creating, of course, the input data from the host, but you can typically think of having this as a data target or an interface level target to create the content of these particular items. So when we are looking into these three elements, so that's really, well, it's 2 HLS kernels, 1 CPU level program, and the AI engines. What we have to do then is to define this kind of linker step that I was mentioning before. And the linker step by itself actually is created by the settings in our design. So the linker step picks up all of these items before, or at least I can describe to list them up in here. And I can basically bind them together in one executable or one library level file, which is then a particular file format that Xilinx is using to combine these things. And it basically holds inside it there the configuration data for the AI engine level, all of the HDL level IPs, and finally also the overlay bitstream if you have them. And you can bring the ideas together, what we saw before. There's a description that basically picks up on these particular kernels, and you can claim, like, when I'm having this memory mapped to stream interface, where does it stream the data to, and the other way around. So basically, this is such a description line. That seems a bit cryptic at this point. We were claiming, or we were asking if we get at some point a more graphical interface to do this, but right now it's not available. So you have to take care about that, but it's not that, yeah, it's still okay to do these things by hand. So when I'm actually building the system level design, let me see if I can find it from here. It actually creates a new top level of your design. It basically picks up on your descriptions from the different modules, like the AI engine, all of these kind of things, uses this as a constraint to actually map the hardware against it. And what we are doing in this case is then really the system project at this point brings the hardware, build hardware link, binary container. The system level project, this redefinition of things, brings actually the new top level into a new Vivado design. So basically this complete software design flow that we were showing before, this one will basically define a new top level by the aggregation of these different elements. And you will then use Vitis to create a new top level that gets fed into a Vivado build under the hood. So what we are doing is kind of a remote controlled exchange or change to your particular items. Let me see, we got the design already. That looks like it. So I'm picking up the block diagram where you saw before we didn't have too much interesting features in there. But now with this build of the elements that we saw before, you will see that, well, known people or people who know that technology may know. Before there was no data interfaces to the AI engines, for example. So this is what came on top. And we didn't have this Vitis region block overall. The Vitis region block, now you won't be wondering too much, is actually holding our two nice HLS kernels in this place that got automatically hooked up with the originally empty platform. So that's the way that we need to think about these designs in Vitis. And that would be like already by its own right, putting you into the position to actually build something that is completely standing up to get a complete design out of these devices. What we have on top there is still the capability of, we can run these different items. So far, when you go back to this approach, what you would have to deal with, you would be able to use QEMU to run the C code to test your C code performance. You would have an emulation level for the AI engine to simulate your AI engine performance and everything like that. And you would have the traditional cycle-based simulator for the HLS side, or for the HLS output rather, to have a validation of your HDL code. So these would be independent modularized verification validation, right? But in the complete system, it used to be pretty difficult to get the proper items to talk to each other, and that's systematized in the complete setup now. So we have the capabilities of system simulation on top of these items. So this means in the end, when you think about it, it's still the same compilation flow. So when you look into AI engine sources being used through the AI engine compiler, you have the V++, that's the Vitis compiler in the widest sense for using HLS behind the scenes. And you have, of course, any kind of additional C code that gets used as a standard ELF for your operation. So all of these items need to go together. libADF is the, well, seminal name for AI engine artifacts, or items are there as a standard output for C or whatever kind of elements you want to use. So you have a different elements in there. O could be also the object code for the kernels, which means the RTL level that you want to package together. You can still also figure out the RTL level to do that. That's pretty straightforward. And in this case, what you get is a complete system that would be there to run the individual emulations or individual simulations. But as you can use the Vitis toolchain to combine these, it would still operate the complete design. So what we get from it, you would basically get your system linker creating the hardware. You get the complete XSIM that you can compile against, and you can write this as a new platform out there, and you would basically be able to start these things in Zynq. So I may try to just show that as a last step rather, from that perspective. So we had this kind of design. So our complete Vitis design within these elements. I could start the, say, like system level project, and what you see from it as a target emulation, it would already say like start emulator. Now, I think somehow the setup broke just a minute ago, again, just as typical for the webinars. So I have a sidekick backup for running it from the command line. And that's the important thing. So what you would be able to do, you would be able to start the emulator. And what we expect to see in a second is really that the complete design comes up. Whereas in the end, when you are then able to hook up your development environment against it, you would also be able to debug applications in this context of the emulator. So what I'll try to do, let me just go there. This is where it actually worked. I'll try to launch it from the command line from the outside on a different design, not the one that I was building there, but hopefully you can believe me that this is the same thing sooner or later if you get a clean buildup of things. So when you create these items, you will be going for also getting created these kind of startup scripts behind the backbone. So basically what I'm doing here in this case, I'm just starting up the hardware emulation of this complete project, which consists of all of these items that we saw before. So it will start the QEMU to ramp up the systems, because these adaptive SoCs will always start from the PS part, always start from the CPU. So the very first steps that you do into your design will go through the CPUs. And this is why QEMU is the central hook point for these kind of simulations. And once it's done, I was asking it to basically bring up the graphical co-interface now, just to be a bit more impressive in this case. What it does, it boots the complete design. It detects that there's a bit stream in there. It would basically pick up the Vivado XSIM, in my case here, in order to co-simulate all the RTL level, which means the cycle-based simulation will be carried out again. So what we saw from our interface on that perspective is already we have this guy, and we have this guy running. Well, it's not quite running, but hopefully we will be there in a second. And that's then the basic starting point what we have. When we look into the shell that I was starting the emulation before, this guy simply just waits for the simulation to go on. But what you will see, as our design is a Linux-based design, it has a complete SD card with it. So when we go on processing on the CPU side, it will ramp up a complete Linux on my side. You will see that this boot stuff comes up through the terminal level as well. So I'm not quite sure why it's that slow at this point, but hopefully we will be eventually there. What we can do, since I will catch up with that later on, we can simply just go into the benefits of that kind of thing, which may not be immediately clear at this point. So when you go back to this idea of the system project combines these different distinct targets that we had under our discussion before. So you have the AI engine things that need to be running somehow, being fed with data, giving you results. You have the programmable logic that basically is there to support your functions and also needs to go input to output data transfers. And you have the processing system that basically responds all in the way that you want to do. When you do modular tests, you will always be there to figure out what the individual function is doing. But when you can overlay these items or the results of all of the things running in parallel as in your mission mode, you will finally be able to identify certain processes within your complete design. And maybe there is obstacles that are only there when you have concurrency between different cores or different contributors, and not so much the actual design by itself. So when we look into it, basically what you see in here, if you do such a complete system simulation, you will be able to trace your overall transaction level of the CPUs, like when is this guy requesting a certain memory portion, when is it writing to. You can see your PL kernels in here as well. That would finally show like when they're accessing data, when they are processing, and also you would be able to combine your AI engine level reports in that kind of thing. So what I can see is always a very distinct time trace, for example, of all of the different contributing partners. And the same way I can have correctness and printouts from my PS software. So the idea behind it basically is, let's go back, hopefully we're there now. I need to get myself there. Yeah, so what we're in the situation that I said before, we have this complete data set of things that are basically there to run against the simulation that we have. So I'm just picking up on a certain design level. It doesn't make too much difference right now. Well, I can use this and basically say, like, what is the interfaces to my AI region? So I can simply just pick one of the streams. In this case, it would be the output stream of my complete graph that we saw before. Remember, this graph has an input, one input and one output. So what I have done now, so the complete startup was running the emulator first place, then it realized that it has to wait for the simulator to be in parallel. I will simply just run this guy for, no, I don't know, it's too much. So like I want to run it for 80 microseconds, for example. So I'll be simply just executing that, and you will see that the cycle simulator by itself simply just clocks. Like it starts to clock anything, whatever, but there's no transmission of data because the partner is not available. So when I'm going there, you see that this now has started to move on, which means it boots the SD card Linux in the emulation. And at some point, it will be eventually end up giving me the prompt. And if I'm having the prompt, then I can execute this host code that we were creating in the Vitis project. You just see it there. So you get this kind of host execution. So my program, I will find hopefully in the SD card an ELF for the Linux side that's called host. And I will hopefully be able to pick up on this binary container thing that we were seeing before to actually feed it into this host operation. And if we are lucky, then we should hopefully see the complete waveform access of this very, very short demo thing. Let me see how we are there. It's only a few seconds more. So it's already auto logged in. So that's one thing that we created there. And now we should be available. Yeah, so what you see is simply just got a complete directory, the mount directory, where the fat partition is mounted into the Linux side of things. And what I should be able to, it should, but it doesn't. Okay, nice. Okay, let me just jump over to the actual PC because I'm remotely connected. So that would mean that I have a better chance to enter the stuff that I want to enter. Oh, no, it's not. Now that's bad. I'm not quite sure why it would be hanging through that line now. Okay. So at some point, the interface has been stopped to work. But what you will see, what you should see from that perspective is that you will basically find, if I would run it now, that the transactions that we were programming into this host code would basically appear on all of these items. So maybe I can add some screenshots to the video later on to really do that, because right now it just doesn't. Let me see. I don't get access to the shell at this point. That's not with the design basically, because it worked just right before the webinar. It's more or less about the interface for me connecting remotely and locally together. So that's the good part. But hopefully it's kind of interesting, or from that perspective, okay, what you can see there, because you have in my listing, you have the host and you have the binary container that I want to add as an argument into the host. And then it would go through like setting up these kernels, setting up this complete system, and basically kicking off the operations. So this is where we wanted to basically work from. But it's already kind of good to see the boot of this complete system software side in the emulator. And while it waited for the, maybe it's okay. Why? Maybe that's the trick. It's just, I was just too slow before because I was talking too much. Oh, yeah, that's good. So what you see there now, that's really the messages of my driver level in our complete thing. When we are lucky, we should see at least some actions going through there. That's my kind of setup. So you see something happening in there. That's the input side, and you will see the output side being responding also in a complete fashion. So what I have established here is really I'm running my emulated own build host code together with the binary stuff that I was building, the bitstream stuff that I was building, and it would finally end up creating the particular responses in there, and I should be there to see results. So that's kind of how far we could have gone here in this case. Hopefully that kind of saves the day at some point. Okay, so that means in the end, just summarizing, and I was actually promising to Anna that we should be good to go within a few minutes more for questions, but we will see. We have the adaptive SoCs that would be very important to be kind of understood as a system of things. You would basically try to map out particular tasks to the best working engine that you have. You try to build your designs based on these abstractions of the modules first place with functional closure first, but the combination of everything else would need to really go through this kind of adaptive process, like this Vitis unified IDE that has the centralized linker stage that gives you the complete images. And finally, you would be there to analyze the coexistence of these different elements in kind of the overall scenario, and finally end up with even a tool flow that allows you to run through a good part of these designs without any like hardware, physical hardware. But also what's important to note on that thing is that if you have a development kit for these kind of adaptive SoCs, it's pretty easy to try out very particular customer specific things on these kits before you need to go into your own hardware. So I think that's where I wanted to end up at this point. Let's see, Anna, do we have?
Yeah. So first of all, thank you very much, Alexander. We have had some questions come in. I think we have a little bit time for some. I will start with the first is, what does CIPS exactly do?
It is the PS system per se. So when we go back to the initial graphs, let me see if I can bring that up again. What is the CIPS system is everything that's under the processor system here, plus the additional configurations of some of these parts. Mostly you will have control interface, that's the CI part. That means it is kind of governing the board bring up, the device bring up, and then it also has the PS system processing system as the cluster of the ARM cores in the different versions. So the CI part was added because actually this platform management controller, which used to be the PMU on the Zynq Ultrascales, has been separated as a qualified separate item. Okay.
Okay, then I will read another question. Can you direct to the relevant guide to create the system simulation script that you've run, or perhaps shortly cover the contents of the script?
Yes, let me see if I can find it out of the way. Let's see, otherwise we will simply just go through that. But there is particularly, if you look into the QEMU arguments, there's a particular guide that holds these things. So the script basically is really just that involved because it has this kind of, not quite sure if I find it out of the box. It has this kind of large number of parameters, and these are all mentioned in this particular guide. Maybe I have it even there. That could be, nope. But I will definitely put it back into the mails that we have in there. So when you look into the QEMU command line arguments, you will find them in the Xilinx documentation, and this is where these things are set up, and it's really a lot of things. So it's always a good starting point from that perspective to get this thing auto-generated, because the compiler toolchain creates it. And then you have all of these kind of special links, like how do you join up the network interfaces into these emulation processes and so on. Because if you get mixed up there, you can have dangling processes, and that can be very interesting. So I know it's there, but I'm not actually having it at hand right now.
Okay, then I think I will, one last question. As I mentioned before, we will follow up on you directly via email, but I think we cannot answer all questions for now. But the last questions I have here, I think I would like to ask if the software kernel correspond to the hardware tiles shown in the slide. I don't know if you know what she means. Yeah.
Nice question. So that actually goes to the AI engine, whereas you have the current setup of the software is like you're qualifying a function to be compiled against one particular AI engine vector processor. If you want to split the function between different vector processors, you will have to rewrite your C code at this point. What it can do from a compiler perspective, it can combine two different functions running on one vector processor. Well, it's simply just combining a sequence of these functions in this case, particularly, right? So it's actually something that we are waiting for from the toolchain perspective to have some kind of support dividing functions between multiple cores. Okay.
Okay, so I think we will contact the other questions afterwards. And thank you all for joining us today. For you, the broadcast will stay open for the next 5 minutes, so you can still write your questions and we will contact you afterwards. Then your feedback is really important to us. So after you end up the webinar, there will be a brief survey pop up. So please leave us your feedback and some other infos for you. We will have other webinars coming up. So in October, there will start a webinar series about the POC library and new features. And we will have a new webinar at the end of September. So please have a look at our website. You can see here the QR codes, especially for the FPGA conference, save the date for next year, and other things coming up. So thank you all again for attending, and have a great day, everyone. And goodbye from my side.